Please settle down. What this really means is that I'm not going to get to everything that I intended to cover today. This is still, we are still continuing with our still revision of linear algebra. And the classes in two halves, the boring half and the less boring half. And because of the delay, I'm just trying to get the board. We will have polls as before, but the polls are going to be on, they're going to be online. The Google Forms, there are URLs for the polls. You're going to have to go to this. Your laptops will be shut in class. Every last one of your laptops will be shut in class, except for the polls. Your phones will be switched off unless you're using it for the polls. Because it's my experience that if I went into that detail, 80% of you will use it for real purposes, notes, and there's one person in the corner looking at YouTube or Facebook or what have you, and that one person is disturbing everyone around themselves and tremendous distraction. This will be a dumb classroom. Everything about this except the lecture is going to be dumb. And the only time you get to use your devices is for the course. So without further ado, let me begin. Any questions from the last class or the quiz? Okay. Now, I'm going to ask you questions as the class has been walking up and down. Yes.
I had a question regarding matrices and how they are put into transformation. So if we have a 3x3 matrix and let's say we have a 3D vector and we're multiplying it by a 2x3 matrix. We discussed that that's equivalent to squishing it into a reduce. Or let's say we have a shape that we're multiplying by a 2x3 matrix that's equivalent to squishing it. So how is that different from multiplying it with a 3x3 matrix which has a determinant 0? Isn't that also like some sort of squishing that's happening?
It is. So we said that there was a difference between the physical space and the embedding space. Remember? And so when you're multiplying it by a 2x3 matrix, it's going to end up in a two-dimensional. Its rank is 2. The physical and embedding space for the resultant matrices will still be the dimension of the. If you multiply by a rank 2 to the 3x3 matrix, the resultant is going to be in a 3D space, but it's actually going to be two-dimensional vectors. Right? That's what it's happening. So, quick recap. I think we learned a few things. We learned what vectors we revised what vectors and matrices are. We saw that signals could be represented as vectors. Images are often represented, can be expanded out and represented as this. We could have time series data sequences of vectors we stack together and now becomes a matrix. There's a sheet of paper. They pick up a sheet of paper and please make this a matrix. There's a pen on the floor. There's a pen. And images are matrices, right? We saw that matrices can have 3 different interpretations. One of them is as a transform. They operate on a vector and generate a new vector. So they transform the vector. And more generally, they operate on a space and generate a new space, which is they transform the space. But then we also saw that they are data containers. They just pile a whole bunch of vectors into a matrix. It's a data container. And now the properties of the matrix tell me something about the data. And then finally, we saw that we can begin mixing up the columns or the rows of the matrix and generate entire spaces. So matrices are space generators. We looked at various products of matrices, operations on matrices and vectors. One particularly important one that's going to appear in place is the inner product between two vectors. And Manohar, how did we define what it did?
The similarity between two.
The similarity between two vectors, right? How much of one vector is it? How much of one vector the other one explains? And so we saw that we had 3 nodes represented as spectra, the C, the E, and the C in the next octave. Then which of the two are going to have the lowest inner product, highest inner product? Anyone?
The C and the higher octave.
The C and the higher octave C, because physically speaking, the frequencies are going to align. Whereas if you look at C and E, the frequencies, very few of the frequencies would actually align up, which is why the inner product is going to be bad, right? So again, trying to give you a physical interpretation of all this. Yes. Your very first quiz of I'm going to give you 60 seconds on my watch, on my phone. And 10 seconds, note the copy, the URL, and URL is the same through the lecture. Note the pattern. That's MLSP 23, right? That's the course. The date 0905 and full number 1. Ten seconds, guys.
It says I need permission, I can't access.
Pardon me?
It says I need permission, I can't access it.
It says you need program ready.
Yeah, I'm trying to switch, so.
That's okay. I'm not going to be penalizing you for these things, right? Anyway, so do we want to answer the question? Which of the following is true of the matrix? Of a matrix? NPI transform. Yeah.
Yeah.
Can it be a data content?
Yes.
Sure. Can be a vector space construct. Can it be an element in a vector space? Can a matrix be an element in a vector space?
Yes.
We saw all 4 would be true, right? What about the second? What is true of matrix multiplication? It can be expressed as the sum of outer products of columns of the first matrix with the corresponding rows of the second matrix. Is that true? Yes or no?
Yeah.
Okay. It can be expressed as the matrix of inner products of the rows of the first matrix and the columns of the second matrix.
Yes.
Kumar, is that true?
Yes.
Yes. The third one, the rank of the products is not greater than the lower of the rank of the 2 matrices. Is that true? Why is that true?
It cannot increase in dimension.
You cannot, if anyone shrinks the dimension, the next one cannot recover the dimensions, right? So the rank is always going to be no greater than the rank of the lower of the 2 matrices. And if both matrices are square, then is the determinant of the product of the determinant? Yes or no?
Yes.
Why?
Because they can be curious to come.
It's just scaling the area.
It's scaling the volume. It doesn't matter which order you scale the volume in, the net effect on the volume is going to be the same. The resultant shape may not be the same, but the resultant volume is always going to be the same, right? So this is what we saw.
What if it's not square? Yeah.
If it's not a square matrix, then what's the volume going to be? What's it going to be? What is the volume of this piece of paper? Zero. Thank you. Right? You're going to squish it down. Right? So, okay. So we're going to look at matrix inverses, projections, eigen decompositions, and singular value decomposition. The most fun bit is SVD. I'm going to keep it till the very end. I'm hoping I'm going to get through all the way to it. I'll rush through the rest of it. A matrix transforms an n-dimensional object into a different n-dimensional object. It would start with a sphere, it makes it an ellipsoid. What transforms the ellipsoid back to the sphere? The inverse of the matrix, right? It is an inverse transformation. So if I have some t which transforms one object to the other, t inverse is going to transform it right back. And so here's what you would have. I can transform a sphere with a matrix, it becomes an ellipsoid. I can transform the ellipsoid with the inverse of the matrix, it's going to become a sphere again. If I transform, so what does it mean? What is the net operation? What happened when I performed the one after the other? Identity, nothing happened, right? So T times D converted the sphere to a matrix, ellipsoid. T inverse times the ellipsoid converted it back to a sphere. So T inverse times T must be an identity matrix, right? Does this necessarily mean that T times T inverse is an identity matrix? Yes. I challenge you to prove it. It turns out that proving that if T inverse times T is I, also implies that T times T inverse is I. It's surprisingly hard. But then, if you look at it this way, this is a sequence of operations, right? T times T inverse is nothing. T inverse times T is going to convert this ellipsoid to the sphere back to the ellipsoid. So it's an identity. That's what holds, right? And matrix inversion provides a way to undo a linear transform. So undoing a transform must happen as soon as it's performed. So here, for example, if I think of A as a data matrix and B as a transform that transforms it from the right, then you're going to get a transform data matrix C, right? So if I want to undo it, I must undo it immediately after I transform it. So A times B inverse is what must happen. I cannot stick something in between. So it says that A equals C times B inverse. Right? Something that's right multiplied must be right multiplied by the inverse. Similarly, if I think of B as the data matrix and A as the transform, then I would get that B equals A inverse times C because I've transformed B by A. I have to transform it immediately by A. Now there are two different things going on over here. I have two objects. One of them, I can think of them as a coupling of transforms, but it's often more convenient to think of it as something holding data and something transforming it. And these are perspectives that we will use with the course. And so, what is the inverse of an identity matrix? An identity matrix is nothing. The inverse is also very different, right? What would the inverse of a diagonal matrix be?
Diagonal methods.
Speak up, guys. There are people sitting out there in Silicon Valley. They have to hear you, right? So when you answer questions, please make sure that your voice carries 6,000 marks, 3,000 marks. What's the inverse of a diagonal matrix?
But one by return of the inverse.
So the inverse of a diagonal matrix is going to be a diagonal matrix also, right? What did the diagonal matrix do? It scaled the axis. So you're going to shrink the axis inverse, by the inverse of the original scaling factor. So the inverse of a diagonal matrix is a diagonal matrix. What is the inverse of a rotation matrix? You rotate it back, right? If I rotate something 30 degrees this way, what is the inverse operation? We're going to be rotating it back 30 degrees, right? We know a rotation can be thought of as a matrix. Now, what is the relationship between the matrix that rotates something by 30 degrees and the matrix that rotates it back by 30 degrees? What is the relationship between the two? Constants.
In the side term will get until conjugates.
The direction.
Come on, guys, you done this in college, right?
Minus cos theta session.
You're giving me the trigonometric equations. But from a matrix perspective, what do you think of that?
Negative.
It's just a transpose. Think about it, right? And you can do this, you can see this pretty much anywhere. If I've got a matrix which rotates it by 30 degrees, the matrix that rotates it by minus 30 degrees, same thing with the diagonal split, we're going the other way. So you can work this out, but intuitively it makes sense. Right? If you're rotating it, if you flip the coordinate space, you're going to be rotating it the other way. So the inverse of a rotation matrix is the transpose of the rotation matrix. Everybody clear about that? Right? You don't need to understand it, you need to memorize it. So will time deficient matrices have inverses? Why not?
Unrecovered capacity.
Unrecovered loss.
We cannot recover the last image. Right? If I take this chart and if I squish it down to a little flat piece of that object, then I cannot look at any point on that object and figure out where in the chart it came from. There were many values that got squished onto that one point, right? So it's not possible to go back from the flattened object, which means that rank deficient matrices cannot have inverses. So in sum, the inverse of the unit matrix itself, the inverse of a diagonal matrix is diagonal. The inverse of a rotation matrix is going to be the transpose of the matrix itself. And rank deficient matrices don't have inverses. So far so good. So this is what we're going to the boring stuff. Anyway, have a nice work. Let's start block one. Yes.
Assuming the URL back links to the stage.
Okay, guys. Because you have a URL problem, Prakash. This is going back to the first call. Correct.
Because it has to be true.
Oh, that's me too. I'm sorry. That's item 2 up there. Yes. Okay. So let's start this call, right? We've had okay. Is the first statement true or false? Second one. Okay, that was easy, right? We spent way too much time on that one. So now let's go back and look at inverses in terms of simultaneous equations and try to understand what happens. Again, you've seen all of this in class. In some class, given a transform vectors, what does an inverse do? It's converting a transform vector back to the original set, right? So if that vector x has been transformed to the vector y, and I'm giving you the vector y, and I'm giving you the transform, I ask you what is the vector x? That's what it is about, right? I can write it out as simultaneous equations. So I have y, which I written as c, and the x vector x I written as x, y, z is going to be a transform. If I just write it out component by component, there are equations, right? Each component on the left is a linear combination of the components on the right. If I have, what is the condition for me to be able to solve this set of equations?
What should do?
First thing, I should have as many output variables as number of input variables at least, right? And then the matrix must be inverted. So the process of inverting the matrix is basically just that of solving the simultaneous equations, right? Now, when I have rank deficient matrices, let's take a specific case where my matrix is 2 cross 2. It's got 2 rows and 3 columns, right? So now my transform vector is 2-dimensional. My input vector is 3-dimensional, right? How many elements will my matrix have? What is the matrix size going to be? You guys, you are the man. You are very honest. So I'm going to come out there and ask you. So what is the size of the matrix got to be?
The original matrix is 2 by 3.
I'm saying the original data are 3-dimensional. I transformed it to 2-dimensional data. So what is the size of the transform? 2 by?
You got it 1 dimension, 2 by 1.
It's taking it from 3 dimensions to 2. Okay, guys, see you in the corners.
3 by 3.
You in the corners.
Hunger.
Okay, what's the answer? 2 cross 3, right? You've gone from 3 dimensions down to 2 dimensions. The matrix is going to be 2 cross 3. Everybody gets that? Right? The size of the matrix, the number of rows is going to be the dimensionality of the output, number of columns is going to be the dimensionality of the output. Again, nothing new, you should know this, right? But then if I try to go back, what happens? I find that I'm given 2 components and I'm given this. And so I'm trying to go back from a 2-dimensional vector back to a 3-dimensional vector. Can I do that? Because I've taken my sphere and squished it to a circle or an ellipsoid, right? And so at any point on the ellipsoid, that could have come from various points on the sphere, so I cannot actually go back. Does it mean there's no answer for the inverse?
Infinite.
It means there are many answers, right? You cannot say which one it is, which is why, when I write out the simultaneous equations, I'm going to have the two output values, A and B. The X, Y, and Z are unknown. The transformation matrix is given, right? And so can you shut your laptop, guys? Please. Okay. So, okay, laptop, guys, there. Hello? Can you please shut your laptop? If you must work, you can go out. I'm happy with it. Okay, so this is that's the rule. So can we solve this? I have two variables on the left that I know, and I have the t terms. I don't know what x, y, and z are, right? Given a, b, and all the t terms, can I get x, y, and z?
Yes.
Yes.
Infinite solution.
There are infinite solutions. Why? Because I have more equations, more unknowns than equations, which is why you cannot actually invert it, right? Same thing. If I have transformed a two-dimensional object into using a 3x2 matrix, what happens? What would happen? It's still going to be, is the object going to suddenly become three-dimensional? No. So what will happen to it? It's going to be a two-dimensional object in 3D space, right? So now, if I give you a point in that 3D space, can I tell you where it came from in the original 2D space?
Yes.
Yes? Are you sure?
Yeah.
Yes.
You didn't lose any information.
Pardon me?
You didn't lose any information.
Actually, a point in the 3D space, and it doesn't know where it came from in 3D space. Does every point in the 3D space have a corresponding 3D equivalent?
Yes.
No.
Yes.
Does it?
No.
Tell me, guys. Shafshi says, what do you not know? Okay, you know, right?
Actually, like many points in 3D space can be correspond to one point.
Is that right?
Yes.
Angad?
Yes. Any point.
Seriously? Okay, what is the pre-image of this point? Where in the original space did this point come from?
Oh.
Did it come from anywhere? No, right? So now go back and answer my question. Does every point in the 3D space have a pre-image in the 2D space? No. Does it, Shashi? Yes or no?
No.
Okay, everybody say no about me, please. 1, 2, 3, go.
No.
Right? I don't even remember it. And so here's what you have. We have points that cannot go back. Because they were not, when I take this sheet of paper and I transform it, this sheet of paper goes into my 3D space. Anything that's not in this paper was not in the original space. Right? And so it doesn't have a pre-image. Make sense? Yeah.
Why you can just project it to the plane?
If you project it to the plane, is it exact?
But
But is it exact?
could be.
But could be. So how do you know that it's exact? If I go back and then come back again, should I end up at the same point? Would I? I wouldn't, right? So that means that's exactly why you have this situation, right? If you look at it in terms of simultaneous equations, I have three-dimensional variables that are two-dimensional variables that I'm trying to estimate, but I have three equations. I have an over-determined set of equations. Are over-determined sets of equations solvable?
Squares.
You can get a least square solution, but are they solvable exactly? No, that's what we mean. There are points in that space which don't have a pre-image. Make sense? Right? So again, things that you have to think of.
Like for the specific plane, there could be an exact solution.
There's some points. The points on the plane have exact solutions. Everything that's not on the plane doesn't. Right?
Yeah, part of them.
Okay, so In this case, if I ask you, because I force you, I'm an engineering manager, and I say if you don't give me the inverse, you're going to get fired. Then what would you do? There's a magical operation called the pseudo inverse, right? What is the pseudo inverse? The pseudo inverse is the best guess operation for the inverse of a matrix that doesn't. So when you can't really invert P, you perform pseudo inverse. What does the pseudo inverse do? As far as it's your best guess. Think about it as a best guess. We'll see what kind of best guess in 2 minutes. But as far as your operations are concerned, you can always replace the inverse by the pseudo inverse. And if the transform is exact, if Y is an exact, has an exact image, then the pseudo inverse will be the same as the inverse. If the transformation is inexact, like in the overdetermined case, then you're going to get a pretty good decent approximation. So the pseudo inverse, often represented as T with a superscript of plus, but also written as P in, is the inverse of a transform that cannot be inverted. And it follows the same rules as your standard inverse. So if you're right transforming by a matrix, if you want to undo it, you have to right multiply by the pseudo inverse. If you're left transforming by a matrix, if you want to undo it, you will left multiply by pseudo inverse. Now, what can you tell me about the shape of the pseudo inverse? Suppose I have my matrix T of this shape. What is the shape of the pseudo inverse going to be?
Shape of its transpose.
It's going to be its
Shape of its transpose.
Y. Why is it going to be the shape of the transpose?
Preserve the line.
We have to preserve the convention, right? So this guy is taking something that's from 3 to 2. The pseudo inverse has to go back to 3. So it's got to be 2 to 3, right? Similarly, if this matrix was like so, what would the shape of the pseudo inverse be? It's going to be right so, right? Because it has to restore the dimensionality again. Thinking in terms of shapes, it's very convenient, and in terms of size. The pseudo inverse has to be the same shape as the transpose of the original transform, which is why when you have a square matrix, the inverse has the same shape as the matrix itself, right? Now, what is the pseudo inverse? Now, if I have a bunch of underdetermined equations like this, which is to say, I have gone from 3 variables down to 2, correct? So when I go from three dimensions down to 2 dimensions, it's like saying I've taken this entire sphere and I've squished it down to an ellipse. Every point on the ellipse has many, many points on the sphere which could have explained it. So when you try to say, if I give you this set of underdetermined equations, which is to say I'm trying to undo a transform which reduces the dimensionality, there are infinite answers. And the infinite answers will lie on a, what kind of surface will they lie on? 3 dimensions.
Here.
3 dimensions.
On a place.
They are going to be on a hyperplane, right? So if my transform from 3 dimensions down to 2 dimensions, then there's an entire line of values in the 3-dimensional space that collapsed onto a single point in the 2-dimensional space. Because the dimensionality of the line plus the dimensionality of my output space is the dimensionality of the input space. If I have a 3-dimensional space and I collapse it to a line, then every point on the line, corresponding to every point on the line, what will you have in the output space, in the input space? A 2D plane, right? I take a 3-dimensional object, I collapse it, I get a line. So I've gone from 3 dimensions to 1, right? It means there are 2-dimensional planes over here which collapse onto each point on the line. That's how the dimensionalities sum up, right? So in this case, when I have an underdetermined set of equations, the solution is going to be an entire plane. Any point on this plane can be the inverse of the point that you're looking at, right? I've gone from 3 dimensions to 2 dimensions. Now I'm giving you xy, I'm asking you what is the original, or I'm giving you AB. I'm asking you what the original xyz is. Xyz could be an entire plane, right? Yeah. So now, clearly this is not a unique answer, right? There's an infinity of answers. But now I'm your engineering manager. If you don't give me a unique answer, I'm going to fire you. How would you give me a unique answer? What would a reasonable guess for unique answer? You tell me. That's what's a very good answer, right? You need an extra criterion. Can you just pick a unique answer out of infinite without extra information? No, right? So you're going to need an extra criterion such that out of this unique set, there's an infinite set, there's one value that you can pick. And if the criterion is the shortest one, that's a unique answer. And that's what the pseudo inverse will give you in this case. The pseudo inverse will give you the shortest vector that actually satisfies this equation. This is in the case of underdetermined equations, where you have infinite solutions. What do you think will happen if I have overdetermined solutions? Like so. Right. So, okay, first. So, what is the formula for a pseudo inverse? You can actually write a formula for a pseudo inverse. You can verify how this works. Now, here's the thing. One of the checks for exactness is whether you can go back and come forward and you end up at the same point, right? If I get a two-dimensional vector and I invert it into 3 dimensions, and then I move it back using the original transform to 2 dimensions, will I end up at the same place? I should, right? Because the entire plane is going to the same point. And so in this case, for the overdetermined case, we have using it. Yeah. So if T is my T has gone from 3 dimensions to 2, right? Is it going to be tall or is it going to be wide? If it's underdetermined, I'm going from a higher dimensional space to a lower dimensional space. What is the shape of it? It's going to be wide, right? So if it's going to be wide, T is going to be something else. Can I invert this? Obviously not, right? Suppose let's consider two T transpose T and TT transpose. Which of these two is likely to be inverted? Which of the two is likely to be inverted?
T transpose T.
I can see the English. Thank you, Amon. Right. So why T transpose T?
Because it's an outer product.
T transpose T is going to look like this times this, right? What's the rank? Is it a rank?
Yeah.
It's not. It's going to be the rank. You see, the rank is going to be the number of columns, right? This is not invertible. The rank over here is just going to be this much, not this little matrix, right? Well, if I look at TT transpose, this is going to be this line times this line, whose size is correct? Makes sense? One. And so T transpose, you have to look at, you must compress it to something that's at the lower dimension of all this. And there's no guarantee that it will be invertible, but that's likely to be invertible. The other one is guaranteed not to be invertible because it's somewhere, right?
We need T transpose T argument.
So this is T transpose T. This is the sheet, right? This is T transpose. This is T. What's the rank? So let's say this is the 2 cross 3 matrix, right? So this is going to be 3 cross 2. This is going to be 2 cross 3. What is the rank of the product? 2. Is that invertible? It's not, right? It's a 3 cross 3 matrix. So you get the idea, right? So, okay, now what does the pseudo inverse look like? It turns out that the pseudo inverse here is going to be, remember the matrix, the pseudo inverse must have the shape of T transpose, right? So it must have the shape of T transpose, but I can post multiply with something and I need to invert it. So without proving it in this particular case, and it's the actual pseudo inverse is going to be T transpose times T transpose, which we saw as this shape and invertible inverse. And we can check if this works by just saying, so the pseudo inverse of T. So if AB is T times XYZ. XYZ is the pseudo inverse of T times AB, right? So E equals T times XYZ.
Yeah, Professor.
Yeah.
We can, in the real inverse, we can exchange the order of T and T inverse.
Here you cannot.
T inverse. So the
Here you cannot. And we're going to see what, right? Yeah, this is again the boarding half of class, so the end will be, right? We'll see what implications these have when you begin looking at real data. And it's so out of time. This is horrible. But so you can see that if I say B equals T times XYZ, XYZ is going to be pseudo inverse of T times B, right? So this is XYZ pseudo inverse of T times B. So T times XYZ is going to be T times pseudo inverse of T times B, right? Writing it down is going to be T times T transpose times T transpose inverse. The whole thing is going to cancel out. It gives you an identity transfer. So it shows you that if you go back and then come right back, you're basically recovering the original data. That making sense? You guys at the back corner? That making sense? Yes. Or that doesn't look like a very enthusiastic nod. Okay. So again, in the overdetermined case, you don't need to worry about the formula for the pseudo inverse. In MATLAB, you can just write P in, right? You can go back and come back, and you're going to come back at the same point. Or, I mean, this is in the underdetermined case. Underdetermined. Sorry. In the overdetermined case, what happens? What does the pseudo inverse do? If I take my two-dimensional object and transform it to 3 dimensions, it's going to be a two-dimensional surface in 3D space, right? If I ask you to find the pre-image of something that's not on the surface, it doesn't exist. What's the best you can do in this case? You can find something on this plane that is the closest to this guy, right? And find the pre-image of this point. That's your best guess, right? Again, think of it as saying, I'm going to go back and then come back. If I go back and come forward again, I want to be back in the original point, but I obviously cannot. I at least want to be as close as I can possibly be. Right? And so that's basically what is going to happen with the pseudo inverse over here. So you will say, I'm going to find the x in my original space such that when I transform it, the transformed point which lies on the space is as close as possible to the point I'm trying to invert. Does that equation make sense? Right? You guys, right? And so when you do this, of course, how would you solve this? Anyone? How would you solve this? I'm trying to minimize this error, right? This is the error between, I'm trying to find x, and I'm trying to find a transform of x that's closest to p. I can take the derivative and equate it to 0. That's what you would do, right? It's a quadratic equation. And so if you do that, you end up with a formula, but there's actually a simpler way of thinking about it in this particular case, which is quite convenient. Again, I can just say V equal approximates times x, because you're trying to find the closest point that will match my original P, right? And so I can say T transpose P equals T transpose P is x, T transpose T times x, right? Because P multiplied by T transpose on both sides. And this guy is going to be, again, remember T is 1, right? So T transpose T is going to be the small square. It's going to be inverted. Correct? And so then I can just write this as x equals T transpose T inverse times T transpose V, right? Which tells me that this term here is my pseudo inverse. Right? Yeah, pardon me? That's my way of writing transpose. That's how I write transpose. Sometimes it looks like a -1. Anyway, simple stuff, right? So underdetermined case, an exact solution exists. It's the least square solution. In the overdetermined case, the solution does not exist. The solution is an approximation. This has a consequence that in the underdetermined case, if I go back and then apply the transform, I'm going to get back the vector. So T times pseudo inverse of T is going to be identity, right? In the overdetermined case, it's an approximation. So if I go back and then apply the transform again, I'm not going to come back to the same point. I'm going to come back to the point on the plane which was closest. So in this case, T times pseudo inverse of T times V is not going to be the original one. Okay. So again, T times pseudo inverse of V is not the identity matrix. So for the underdetermined, T times Pn is I. For the overdetermined, T times Pn is not I. Let's see what it is. Okay. And so basically, matrix inversion tries to undo a linear transform. The first row shows you the rules that we saw. The second row shows you the same rules with pseudo inverses. If your matrix is not invertible, you can use the same rules as you did for standard inversion, except that instead of regular inverses, you're going to be using pseudo inverse. That's it. So and this, believe it or not, it's magical, right? We can do all kinds of things with it. So much stuff I'm throwing at your face. But then think about it. I'm telling you about how to invert a transform. I give you an X, I give you a Y, I give you a T, tell me X. That's what we were talking about when we speak of inverses and pseudo inverses. Let me give you something else. I don't give you the transform. I say, here's this collection of points. They were transformed. And they resulted in this other collection of points. What was the transform? How would you do it, right? Again, very simple, right? I have all of these X's. They were transformed and they became Y's. What is T? How would you solve this? Matrix. Yeah?
Yeah, see all the x1 to xn as the one matrix.
Yes. Saying something?
X
inverse? It's not going to necessarily be an inverse, right? But it's going to definitely be a pseudo inverse. So I can pack all of the X's into a matrix. I can pack all of the Y's to a matrix. And then Y equals approximately equals T times X. So T equals Y times pseudo inverse of X, same as the fixture applies. So the pseudo inverse is a generic concept when you look at things this way, right? It's very cool. And so, you know, if you're trying to convince your political opponent and you want to know exactly what transform to apply, the pseudo inverse will be. You know, elephants can become donkeys, right? There's four. It's -3, it's not -1. It's copying the wrong thing. I have to keep your ear close.
Thanks for yesterday.
Okay, 10 seconds, guys. Let's stop this. Okay. Who wants to answer the first one? Where on? Is the first one right? Right.
That's the main first one.
The student must provide the data approximately inverse one of this. And it's not on the second statement. Is it right? Also true, the student must can use to undo a linear transform, also true, right? So, Hari, what's the third?
Like I have doubt with the second one.
Yeah.
So it's not exactly an undo, but
It's an approximate, that's why there's a double quote, right? So, I'm playing word games. So anyway, but The third one, is that true? Third is false, right? You cannot exactly reckon, you can kind of reckon. There's only one unique solution for the underdetermined case. Is that true?
Yeah.
False, right? For the underdetermined case, it has to be one solutions, right? So this is the only thing that's not true. Wait. Okay, forget the counts. They're fraudulent, okay? So I'm allowed to make mistakes, you guys are not. So where does all of that lead us? Why are we talking about all of these things? In the very first lecture, on linear algebra, the very first thing you said was that a vector, which is a point in space, can be expressed in terms of different sets of bases, right? So if I give you an XYZ standard basis as my basis, when I give you a vector, you have to imagine that the vector actually comes loaded with a set of bases which may be explicit or implicit. If I don't give you the basis, you're using the standard basis, they are implicit, right? And so let's say I have a point, a times x plus b times y plus c times z, right? And then I change my basis and I ask you what is the same vector in terms of my bases u, v, and w. How would you do it? How would you do it? Anybody?
Dot product.
How would you do it? Dot product may not do it, right? I didn't say those vectors are at 90 degrees. How would you do it?
Transformation from
Okay, so here's what I can do, right? I have the vector V, and let me say x, y, z, I'm going to call this just a big matrix X, okay? And the corresponding representation of call this is small vector X. So you're given X, you're given x, y, z, and then I'm going to call the u, v, w as the big matrix B, and I'm trying to find the u. Okay? Isn't this what we're trying to do? Then how would you do it? Come on. Go on.
Just project it and scale it.
You're making a to-do of nothing, right? I can say x times x equals b times u. What is u? We just spent 25 minutes by my clock talking about this.
So it was
What is u?
X.
Azim, what's u? It's going to be b plus x, correct? That's it.
Yeah.
B inverse or B plus, depending on whether it's full set of bases or not. That making sense to everybody? It's not so hard, is it? Once you begin thinking about it in algebraic terms, these things are just so trivial. Once you look at it. Make sense? I didn't have to work everything out. So there is a transform which is going to convert x to u. And that transform is just a pseudo inverse x. I'm not sure it makes sense. So this is not, again, I'm not teaching you anything that you don't already know. Right? Just it's most likely that you never exercise those concepts. And so when I ask you that question in class, you get stuck, but if I put it on an example and gave you 3 hours, you'd probably give me an answer. Right? Nonetheless, right? So now, so I can think of a matrix as a basis transform. I can think of a matrix as a way that converts representations in terms of one basis to representations in terms of another basis, right? Be okay with this? This is another very, very important thing in life as far as a machine learning scientist is concerned. Because, look at this. Suppose I have a whole bunch of three-dimensional data. I can represent the data according to multiple bases, right? I can choose my basis. So long as they span the space, I can use the basis. So now here, all my data lie along that blue sheet, corrugated sheet, right? I can represent the data either according to U1, U2, U3, or V1, V2, V3. Which one makes more sense? V1, V2, V3. How many of you think that these make more sense? And how many of you think the U's make more sense? Okay, explain why. Is he orthogonal? So these are orthogonal also in this case, right? So why did you think the V's make more sense? Okay.
It's kind of normalizing your like plane that we want.
So the V's are actually capturing the surface that your data lies on. And then if you look at the variations along V's, think about it in this way. If I gave you the data, if I give you 3 bases, and if I give you the corresponding components, then I can say, I'm going to give you A, B, and C, right? If I lost one of these, can I still reconstruct the vector? If I give you U1, U2, and U3, and explain the vectors in terms of U1, U2, and U3, and somehow forgot to give you, or decided that I decided that my budget only lets me send you 2 numbers. If I choose to give you U1 and U2, can I reconstruct the vector? No, the thing is completely gone. But then here, if I choose to not give you B3, and I just give you B1 and B2, how much do you lose? A lot less, right? So because this captures the structure of the data. In the V1, V2, V3 coordinate set, values along V3 are always small. You can almost imagine that they are noise. And even if you didn't present it, you get most of the information about the vector system.
Let's say if the data has a smaller norm, that means it captures the data structure.
We are speaking of the entire data structure. The bases capture the data structure. We are not speaking of the norm, right?
Yeah, I mean, generally the norm is super small. That means the basis is good.
No, the norm of the vector is the length of the vector. So we're speaking of the norm along the V3 component. If that is small, the basis is good, right?
Okay,
This tends to be the most important challenge in machine learning. Finding the best set of bases for a given data set is a very serious challenge. And so now, let's say I have magically found these bases, right? V1, V2, V3. Except I decided I'm not going to use V3. V3 is kind of noise. And I just give you V1 and V2. Then, given a vector, how do I represent that vector in terms of its bases?
Multiply them.
New basis vector. New basis vector. Have we just not worked the example out? What will we do over here? If X is my standard basis, right? This is it, right? And if X is my standard basis, I don't even need this P plus. That's better. Put this on the. It's going to put it on the sheet. If I want to go back to the original space, right? B plus is just giving me the coordinates, the U. Correct? I have to quickly multiply by B to give you the actual vector of that place. Does that make sense? If I multiply by B plus, it's just going to give you the coordinates. And that's going to give me U. Right? U equals B plus X is for this. And so if I want to think of the entire representation, C equals B is B plus, right? This is the operation that's actually going to give you the representation of the data on this U basis set, regardless of whether it's a complete basis set which spans space or just a subspace. That makes sense to everybody? You guys, that makes sense? Right? This one is what is called a projection matrix. If I give you a bunch of bases, the matrix that's composed of the bases times the pseudo inverse of that basis matrix is a transform that takes your data and projects it down to the surface. So, for example, if I give you the bases in this 3-dimensional space, I have this 2-dimensional subspace and give you the basis for this 2-dimensional subspace. Then if I want you to project every point on this group onto this 2-dimensional subspace, what do you have to do? I can just take this basis matrix, right? Multiply by its pseudo inverse, etc. in this form. That's a projection matrix. And then when I multiply every point by that transform, you have all going to appear as shadows on this piece of paper. Does it make sense? Right? So, guys, did that make sense what we were talking about? Yes, sir. Yes. Okay. And so, if I were to ask you, so this may become something more interesting, right? I give you a cone like this, and then I just give you this piece of paper, and maybe not the sport, maybe the sport, right? And I say I want the shadow of the sport on this piece of paper. How would you do it?
Sunlight.
Sunlight, yes. The mathematical operation, please. Beautiful. It's a good answer. But what
What the projection on
I'm just giving you the sheet of paper, right? So how am I going to project things onto the sheet of paper?
Sheet of paper into pseudo inverse.
The sheet of paper is not a set of bases. What would I do?
Use a sheet of paper.
You guys, what would I do? Anyway.
Well, you get a surface like.
Perfect. I can draw two lines on this, any two lines on this sheet of paper. And those two lines, so long as they are not collinear, I'm going to completely specify the space, right? Now I have my basis. So basis times pseudo inverse. I can choose any two vectors. And then that basis set times its pseudo inverse is going to give me my projection matrix, which I can just use to project things down onto this plane. So I could just pick any two vectors, W1 and W2 on the sheet of paper. They're going to form a basis matrix. The basis matrix times its projection is going to tell you what the shadow of the tell you how to compute the shadow of every object on that piece of paper, right? Now, all of these are, there are no magical operations of it. I'm still talking about standard linear algebraic transformations that we've obviously performed in all our lives. What do they do, right? And I'm assuming you're getting some intuition of how these things work, or at least you're understanding until you go out of the classroom, right? That's how it works, right? But then, so here's the thing. When I think about projections, if I project everything down, this entire room down onto the sheet of paper, can I project it a second time back onto the sheet of paper? It's the same, right? The projection of a projection is still on the sheet of paper. So which means P squared equals, what is P squared? P squared equals P, right? It's not identity. Once I project it, it stays on this paper. So P, what is P cubed? What is P raised to N? P, right? Regardless of how many times I projected this P. So it's an idempotent transformation. And so, it's a very cool thing. Now, that's so much for math. Let's try to get a physical meaning for projections. I can just choose my bases. And what does projection on the bases do? It tells me how much of the data can be explained by those bases, right? And that can be a very important thing. So I can just choose my bases W1 through WK. And the portion of the data that can be explained by W1 through WK is the projection. So let me give you a physical example over here. I'm going to play you sound if I can. Communist music. Polish Kapolie. There's also an Indian song with the same tune, but this is written in 1919, right after the Russian Revolution. And it's the anthem of the Russian army. So, how many notes are there in this? I think there are several notes, right? It's very pretty tune. But then there are a few dominant things. Okay? So here are some notes that are dominant. So you can hear those notes again and again, right? How are those notes played? So let me consider my first note. If I want to know how much of the music was explained by that note, what do you think I will do? Pardon me? Play only that. Yeah, mathematically, what am I going to do? Project that. I can take the spectrogram and project it onto the spectrum for this node, right? And how do I project it onto the spectrum for the node? That node is my basis. That's defining my space. And now I can project the entire spectrogram onto that basis. And that's going to tell me how much of how that note was played when this music was generated. So here is the note. And well, this is the original music. So actually projected it down onto that and there's some noise to clean it up. Let's hear this. Right? It's only playing those portions of the music where that particular note was played. So that's what a projection is doing in this case. Now, I think it's not. So, I have no idea what's going on. Right? So now, by the way, that was me on my harmonic. Not very good at it. It sounds shaky, right? But if I try to explain, so there's a ghost in the room. If I want to explain the portion of the music that was composed by these four notes, then what would I do? I can make the notes my bases and project the spectrogram onto these bases, right? And so that's my projection. It looks kind of messy, so I cleaned up the low energy functions.
I was read through the handout, but are we expected to like
No idea what's going on.
file encoding or receiving, or are we definitely going to get one file?
Connecting to the Zoom.
Maybe it's just
Are we
someone
going
else.
to
There is someone
receive, like,
asking questions.
Questions on Zoom? Yes. Yes. No, there are people conversing on Zoom, right? Whoever you are, please stop talking, right? So, again, going back, so you get the idea of what a prediction means. Unfortunately, I'm not going to finish again decomposition and SVDs by the end of this lecture. So what I will do is to actually do this separately over Zoom, not as part of the regular lectures, but this is very important. It's for everybody to be here. Okay. Now, how was the note played? Can you tell me how the note was played? The first note. Start of it.
The dispatcher for wisdom.
That's right, man. You're not going to be doing anything more than what I've just covered in the class so far. So can you tell me how the note was played? How would you compute it? Anga?
How do we compute it?
I want to compute the score for that note. How would I do it? So I have a spectrogram S, right? To compute the score for the note, I want to see how much of the music was composed by that note, right? So then what can I do? I can say, find me the approximation. This is my note. That's my, I call my score T, right? And I'm now asking you to find T. What is T going to be? Guys? Can everybody just yell together pseudo inverse? No, everybody together. 1, 2, 3, go 1, 2, 3. Thank you, right? So S is going to be, where will the pseudo inverse go? To the left or right? Left, right? The node is left multiplying. N plus S. Beautiful. Again, we're not doing anything more than what we just covered. So. But I'm showing you how you can figure out how much of the data is to be explained by a particular choice of basis and the manner in which it must be modulated to construct the data. So same thing, if I'm giving you all 4 nodes and I'm asking you the scores for all 4 nodes, what would you do? Pack them all together, I do the pseudo inverse, I'm going to be able to get you the scores of all 4 nodes, right? It doesn't quite that clearly, I'm lying a little bit, There are some assumptions here, but you get the idea of what projections and what are explaining data in terms of bases and what the inverse and pseudo inverse do as well, right? And so now, suppose I give you the score and I ask you the note, how will you do it? So I give you this piece of music, and then I say there are like 20 instruments played over here, and here's how each of the instruments plays. But I'm not telling you which it is. I'm not telling you which note is being played. How would you compute it? Can we have a chorus again? 1, 2, 3. Thank you. Right? So I'm asking you to find n. I've given you t is s. How are you going to find n? It's going to be s plus, right? There you go. So again, you see how that works? Yeah, makes sense, right? So it's all very pretty, right? We look at so many ugly equations, things sort of look very tangled, but then when you look at it closely, it's easy, right? Now, the projection matrix, is it full rank? If I'm using 4 nodes, let's get an idea of what rank is. If I'm trying to explain the music in terms of only 4 nodes, what am I doing? I'm constructing a projection matrix using the 4 nodes, right? Is that projection? What is the rank of the matrix? Who said 4? Okay, did anybody else say any other number? Okay, so you can answer this 4. Why? Yeah. So the point is this: rather than thinking of releasing the dimensionality, there are only 4 nodes, right? Can you, if I project it down, if I transform the data down using the projection matrix, can I ever tell you what the 5th node, how the 5th node is playing based on the result? The information is lost, right? So the rank is exactly how much you think, how much it explains. Right? So that's what here means. Again, it's all very nice to think of it in terms of mathematical abstraction. But then when I give you this music example of music, what is the rank of a projection matrix? It's 4. There are only 4 nodes. But suppose instead of the 4th node, I gave you another thing which is actually a mix of the 2nd and 3rd node. What would the rank of the projection matrix be? 3. Because there are only 3 nodes left in the data, right? So it goes, right? And so I'll sort of skip these fine details. There's a little code. Who has mind by waiting 5 minutes beyond the end of the class? Yes, no. That way I can get through a CD, right? I'm only going to give you 15 seconds. There are only 2 true false questions. Okay, 5. Okay, Justin, what's the answer to the first question? True or false? That's true, right? If I give you 4 nodes, the projection is recovering the portion that can be explained by those 4 nodes, right? You get a feel for that, right? Then if my matrix T is a tall matrix, right? What is Q times pseudo inverse of T? I'm going back to abstraction. Right? What was T times pseudo inverse of T? So think of this. If T is my music, is my matrix of nodes. What is T times pseudo inverse of T? Is the projection matrix that told you how much of the music was explained by those four nodes, correct? Just to give you a feeling, again, once I write the map, suddenly the feel goes away, right? But then you have to think back on the map into real examples in life, because otherwise it won't make sense. Math is very fuzzy. I hate math. I'm really bad at it. But then once you begin looking at it in terms of real things, that makes sense. Right? So T times pseudo inverse of T. If I think of the music example, my tall matrix is my matrix of the four nodes. T times pseudo inverse of T is a projection matrix that projects the data or music onto those four nodes. Right? It's mixing, it's telling me how I can mix the columns of T, the nodes, to come up with the best approximation to the music. Does it make sense? Right? So that last one is very important. That particular question. Did everybody get that point, that last point? Raise your hands if you did. And some of you have not raised your hand, and some of you look positively puzzled. So Ihan, did I lose you? Thank you, right? I like honesty. So what did we do? Think about my example, right? If my nodes are my matrix T, then what are the columns of the nodes? They are my four, the columns of T, they are my four nodes, right? Okay. So when I said S equals, I'm trying to approximate. This is my transcription, say. I want X my score, it's my spectrogram. Then I said X equals T plus times S, right? This is the score. And so my projection, Tx, which tells me how much of the matrix, how much of the music is generated from those four nodes, right? That's T times X, correct? Right. This is because I'm saying approximating. I'm trying to see how best to approximate my music in terms of my four nodes. So T times X must approximate S. So then the X is obtained by multiplying S by the pseudo inverse of T, correct? So T times X is going to be T times T pseudo inverse times S, right? This is my projection matrix, right? And what is the projection matrix doing? It's telling you how much of the data can be explained by the columns of T. Does that make sense? Right? If I write math, it doesn't make sense. Did all of you get that? Right. And so, and then the final bit, I think I'm so out of time. What's the time? 18? Yeah. You want me to go on for 10 minutes, or would you rather I do this on Zoom? Go on for 10 minutes, raise your hand so I can. That's a very small slide. Okay. I'll override anything. Right? So, eigenanalysis. How do you understand an eigensum? What is an eigensum?
Just scaling.
Just scaling, no transformation, not just rotation, right? So, for example, let me play this.
1, 2, 3, 4, 5.
It's my friend Paris. Now we put into a reverberant room, right?
1, 2, 3, 4, 5.
Did his voice change? Right? Now here's a different sound. Okay, I put the same sound, in that room. Didn't change.
No.
One of them was an eigen input to the room, the other was not. Which was the eigen input to the room? The B, right? An eigen input to any transform is an input that does not get modified by the transform. In the case of a matrix, that's going to be a appendage, right? So you get an eigen input, eigen input means. But this concept of eigen applies across the board, everywhere. And so eigenvectors are vectors that do not change upon being transformed. They just sort of become longer or shorter. And so here I've got a whole bunch of vectors being transformed by this matrix M. Two of them did not change their direction. Which two? The two black ones did not change their direction, right? They are the eigenvectors of the transform. Now, here, I took this Mona Lisa image. I didn't, somebody did, and sheared it, right? Did every point on Mona Lisa change? So there is one direction which is an eigen direction, which was the vertical direction, right? Things didn't get modified along the vertical direction. They got modified along the horizontal direction. So what is the red vector? Eigenvector. Is the blue vector an eigenvector? No, right? And so you get an eigen, right? Okay, that transforms. And now, here's a way of thinking about matrix transforms. If I've got a matrix operation on a space, the matrix operation is doing something very interesting. It's rotating the space, it's stretching it, it's doing stuff, it's converting a circle to an ellipse. But there's a different way of thinking about it, matrix transforms, right? So you have to specify the entire matrix to determine how it transforms the space, right? But there's a different way of looking at it. Imagine there is probably two more arms, like standard Hindu god, right? And so now I took this sheet of paper, one pair of arms, grab this sheet of paper like so, another pair of arms, grab the sheet of paper like so, the sheet of paper like rubber, and then one of them stretched it this way, another stretched it along this direction, right? If I had a circle on the paper, would the circle get transformed? It would, right? Because I'm stretching and it along two different directions. Would the vectors on the circle move? When the circle is getting transformed, the vectors move, right? Does every vector move? Which vectors don't move? So once where I grab the paper, if I grab the paper and stretch it, those two stay fixed, right? They may change length, but they will not move. Similarly, the other hand, grab the paper like this and stretch it. Those two stretched, but they did not change direction. And so now the entire transformation can be specified by specifying where I grab the paper and how much I stretched it by. Right? Meaning specifying, so what are the eigenvalues here? What are the eigenvectors? The directions in which I grab the paper are the eigenvectors. The amount by which I scale it are the eigenvalues, right? So that's exactly what is going to happen here. So here I'll be grabbing it in two directions, and you can see that my animation failed. So pretty good, right? And so again, this is a equation you're familiar with. If I specify the eigenvectors and the eigenvalues, I've specified the transform. Right? Can I describe eigenvectors for every matrix in this map? Every square matrix, can I define them in this map?
Only positives.
There is a class, there are several classes of matrices where you're going to think of them differently. So, firstly, here's something. If it's a square matrix, you speak of eigenvectors as square matrix, then if I have a circle which is unit area, if I stretch it along two directions, right? Then the area of the circle is going to change. How much is it going to change? It's going to increase by, lambda 1 in this direction and lambda 2 in this direction, right? Which means that the product of the eigenvalues is the determinant of the transform. Because that's how I'm stretching it by, correct? And so that's one thing you have to think about. And when I rotate a matrix, there's no direction which is fixed. Everything rotates, right? So in that case, you don't have directions there. The eigenvectors and eigenvalues are very complex. Okay? And then there's a very specific class of very nasty matrices called defective matrices. And as it turns out, in the transform that modified this poor Mona Lisa over here, there's only one eigenvector. It doesn't have a second eigenvector. It's an invertible transform, but it doesn't have a second eigenvector. A matrix such as this is called a defective matrix. And our standard response to the defective matrix is to run away from them. You don't want to deal with effective matrices. They're hard to deal with. So, and okay. So that's for eigenvalue decomposition. Now, I'm not going to go over more details of eigen decomposition. Talk about another operation. In eigen decomposition, right? When I transform a vector by a space by a matrix, the eigenvectors represent directions that do not change. They may stretch, they may shrink, but they do not change direction, right? But then, over here, if I transform this circle with a matrix, there's another key way of, and so I can specify the transform entirely in terms of the directions that don't change with the non-directional vector, right? But then there's another way of specifying this transform, key and feature, which tells you how the circle changes. What else about the ellipse tells you something about the transform? The major and minor axes, right? And so when you look at the transform, what you will find, there's a second way of defining transforms. There's a set of orthogonal vectors in the input space which remain orthogonal in the output space. And every matrix transform is going to have this property. There's going to be a set of orthogonal vectors in the input space which remain orthogonal to the output space. These are called the right singular vectors. The ones on the left are going to become the left singular vectors. And so if I have a circle of unit radius, the ellipse is not going to be unit radius, it's going to be, it's going to have a major axis and a minor axis. And so the major and minor axis of the ellipse are 90 degrees to one another. They're also going to be orthogonal to the input space, right? And so singular value decomposition basically tells you which these vectors are. It's going to tell you what vectors on the output space actually stay, retain their handles. What vectors in the input space retain their handles in the output space, and they're going to be orthogonal to one another. Now, singular values, I think the vectors have a whole bunch of properties to them. I'll leave those on the slides, but for you on the slides, but there's a very specific bit. So give me a couple of minutes about SVD, which clearly really matters, right? SVD is going to convert, transforms the right singular vectors to the left singular vectors. The transpose of the matrix is going to transform the left singular vectors to the right singular vectors. There are two key aspects to it. Suppose I give you a vector of unit length on the input space. Now, the length of the corresponding, again, the singular values over here are the lengths of these major and minor axes of the output of the ellipse. The singular vectors are the vectors themselves, right? Now, if I give you a vector of unit length in the input space, what is the longest it can get in the output? Anyway, what is the longest it can get? It's going to be the major axis, the largest major axis of the ellipse, right? And the length of that major axis of the largest singular value. So, what is the smallest it can get? The smallest of the axis. And so, here's a property that you're going to get. If I look at the ratio of the length of the transform vector to the length of the original vector, that ratio is upper bounded by the largest singular value, and it's lower bounded by the smallest singular value. Okay, there's a bunch of properties that result from this. Again, all of that looks at singular values as transforms, but then let's look at singular value decomposition on data container matrices. So I got a matrix and pack a bunch of data into it. So I got a data container. So this will be a bunch of traces, a spectrogram, whatever. And then any matrix can be singular value decomposed into the matrix of left singular vectors times a diagonal matrix of singular values times a matrix of right singular values transposed. Okay, so pretty much any matrix can be written in this manner, including a data container matrix. What does this mean? Then those vectors, so these are all orthogonal vectors of unit length. These are all orthogonal vectors of unit length. Okay, so now when I expand it out, this is what the SVD is going to look like. So your V transpose is going to be this giant matrix where the rows are all orthogonal vectors, right? Your U is going to be this matrix where the columns are all orthogonal vectors. Your X is going to be a matrix of diagonal elements, where the diagonal elements are singular values. Yeah.
What is orthogonal to each other, like U and V's?
No, these guys are all orthogonal to one another. Remember, they're all 90 degrees in equal space. Right? These guys are all orthogonal to one another. They're at 90 degrees in the outer space. Okay. And so this is basically explaining what the transform does, right? Like if you want to see a little more into how this works, look at the slides. But this has an interesting characteristic. When I work it out, remember, what is the product of two matrices? So firstly, when I look at the product of this guy, so this guy and this one, that's simply going to be scaling these columns by these diagonal elements, right? So that's not a problem. And then when I multiply this matrix after it's scaled by this one, it means that the first column of U multiplies the first row of V transpose, right? The second column of U multiplies the second row of V transpose and so on. And then each of them is scaled by the corresponding singular value. So the sum is singular value 1 times the first left singular vector times the transpose of the first right singular vector plus singular value 2 times the second left singular vector times the transpose of the second right singular vector and so on. And let's just order them by the magnitude of the singular vectors. Now, one of the special properties of SVD is that all vectors will always be real and all singular values will also be real. Now, this original data matrix has some energy, right? We all know the notion of energy. It's the sum of the squares of all of the components in the matrix. If I've got a data of real spectral values, they're all the sums of all of the energies. If I've got any other data, the square of any component is the energy, right? And so I have the sums of all of these energies, right? Now, if you look at this guy, these are all orthogonal to one another. This guy is orthogonal to this one. So this is going to have some energy, which is not explained by this one. This term is going to have some energy, and this term is going to have some energy, and so on. So each block has its own energy, and the sum of the total energy in the data is the sum of the energies of these individual components, right? Now, something else. This is a vector of unit length. This is also a vector of unit length. So the energy in this particle product is going to be 1. So the energy of the first matrix is simply going to be S1. The energy of the second matrix is simply going to be S2. The energy of the third matrix is simply going to be S3 and so on, right? So the X is going to be summation I, psi divided by transpose. If I look at this way, then the energy, the first one is the magnitude, the singular value. You have the, you can think of the left singular vectors as the bases, the right singular vectors as formulations, right? And now, what this means is that each singular vector is contributing some aspect to the overall data. And the energy of the contribution is equal to the square of the singular value, right? And so, if I just want to retain most of the energy in the data and throw away the least significant components, right? Here's what I can do. I can look at all of the S's, and if the S's are small, that portion can be completely disregarded without changing the energy in the data itself, right? Because they're very small. Make sense? Right? And so, you're looking last. Okay, so, because those small guys don't really carry a lot of information. And so here is my spectrogram. This is my original music. This was a matrix of something. 974 cross 1020. I have to compute singular value decomposition for this. And those are all my singular values. And you can see there are a very small number of non-zero singular values. The rest of them are really very small, very tiny, right? The singular values themselves. So what I will do is, instead of retaining the entire matrix, I'm just going to retain the contributions of the first k singular components. The first k singular, left singular vectors and their contributions. Okay. So here, if I retain the first 25 highest singular value components, is it any different? Absolutely no change, right? What is this telling us? Yeah. Yes, they say there are only 25 real combinations of notes in this one, right? If I use just 25 combinations of notes, I can explain the entire music. You know what? This is with 5. It's a pretty complicated piece of music, but I composed it with just my 5 left singular values from my data matrix. What does that tell me?
Not just add, it's the production of notes with the.
I just need 5 combinations of nodes to compose the entire music. Right? And I can combine those 5 combinations of nodes in different ways, and that's it. Right? So although there are many nodes in this, the actual number of independent or separate musical elements is just 5 different combinations. Again, what does SVD tell us about data? You get a pretty strong feel for what SVD does when you begin looking at examples. I'm sorry for having rushed through the last bit. I request all of you to go through the slides again. I've gone over by a lot of minutes, 17 minutes, my apologies. But it was either this or we will just. So, don't forget to bring your name tags or next class.